Today I'm going to look at some of the vector noise functions that are available in Affinity Photo's procedural texture filter. I did a previous video on regular noise, but I didn't do one on vector noise yet. And the main reason was I didn't really have a good understanding of it. I didn't know how it was generated, and I used it sometimes, but I still didn't really understand it very well. So I've taken a deep look at trying to understand it, and I think I understand it quite a bit better. So I'm going to look at that and try to explain what I think I figured out with it. So this won't be a video where I go over an example of how to make a cool texture. In this case, I'm looking at one of the sets of functions that's available within the procedural texture filter. If you look at the vector noise functions, there's quite a few different functions with quite a wide variation in them, but they come down to just a couple of categories. The first one is dir, which I believe stands for directional noise. It's a two-element vector. And after some effort, I was able to determine that that has a radius that ranges from 0 to 1 with a uniform distribution. And it has an angle that ranges from minus 180 degrees up to plus 180 degrees with a uniform distribution. So basically they're generating a random number from 0 to 1 for the radius and then assigning a random angle to that based on the range from minus 180 to 180. The udir is also a two-element vector. It has a radius that's always equal to 1. And the random part of this is the angle that ranges from minus 180 to plus 180. The third type of noise, dir3, is a three-element vector. It has a radius that ranges from 0 to 1 with a uniform distribution. And then it has a uniform theta in the xy plane ranging between minus 100 and 180 degrees. It has a phi value that ranges from the xy plane up to the z-axis of 0 to 90. I'm not sure why they didn't go from minus 90 to 90, but they don't. So it only goes in the positive z direction. It does not rotate down to the negative z direction. And then udir3 has a vector with a radius equal to 1, and the xy angle again ranges from minus 180 to plus 180 degrees, and the phi angle goes from 0 to 90 again. In addition to these four main types, there's also interpolation for these. An S-curve interpolation, a sine interpolation, CS, which is sort of the circular interpolation, I means no interpolation, and then no suffix at the end will give you linear interpolation. I've set up a procedural texture filter that includes a wide variety of these values, and I'm going to demonstrate what I just talked about with this. So I have a histogram of the values and a scope of the values here. I have a large number of equations here and some custom inputs to control them down here. I'm going to start with regular noisei, which is the simplest form of noise, and I've got a multiplier on this of I, and I've got an offset of OF over 2 added to this, and that'll allow me to add a plus 1/2 to some of these noises. It'll make it work out just right. This shows the uniform distribution from 0 to 1. I've got my offset set to 0 and the multiplier set all the way up. So that's just what I would expect if I look closely at this, I can see that these are square pixels of noise with a uniform random distribution. Next one I'm going to look at is, I'm going to turn these off. The next one I'm going to look at is the dir of I. So I thought that was the simplest form of that one. I see there's a lot of black squares now, so that seemed a little strange. And if I bring the distribution up to 500 again, now I can see it's clustered near 0. I also notice there are just red and green values. There are no blue values in this vector. If I bring this over to 1, I see I've pushed some off the edge here, so I'm going to bring this down to about halfway here. And there I see I have my values all contained. They go positive and negative for this vector. All right. So that seemed a little bit odd, but then I thought to look at, what is the length of the vector? So if I turn these off and look at the length of the vector and return this back down to 0, offset to 0, and put the scale up to, or the range up to 1, I have a uniform distribution from 0 to 1 again, with uniform noise from 0 to 1. So that tells me that the length, or the radius of the vector, varies uniformly from 0 to 1. Now I'm going to look at the angle. So I thought next, let's look at the angle. So if I look at the angle of this, I'm going to set this, okay, so it goes negative and positive, and I divided this by 360 degrees. So if you look at this equation, in this case, I'm dividing by 360 degrees. And if I move this over like that, then I get a uniform distribution. So that tells me that the angle is going from minus 180 degrees to plus 180 degrees with a uniform distribution of that angle. Okay, so that told me that bit of information. So now I'm going to go on to this udiri and look at that distribution. So that distribution at first looked really strange to me. I'm going to set this back down to 0 like that. So I have this large cluster of values right up here close to 1. And if I scale this and offset it, I can see that it's going positive and negative, but it has a lot of values here at this end, a lot of values here at this end. So a lot at +1, a lot at -1. However, the mystery disappeared when I took the length of that, because I started off with the offset here. When I have this all the way up, it's 1. Move it here, or move it to 0. So that tells me that there's no variation in the value of the radius, or of the length. It's always 1. So that when I have the udir, that indicates a length of 1. Okay, I'm going to turn those off, go to the next one. The angle then is uniform, the same as before. So if I leave this up, bring this over, it has a uniform distribution of minus 180 up to 180. So that's good. Now I'm looking at the three-dimensional vector and dir3. And so this is a vector pointing in 3 dimensions. And if I look at that, it looks like this. I bring the scaling down. If I bring the scale down to 1/2, this is already over. So if I leave this, let's start out with that one. So it looks like that to start with. I can see now it's added the blue component. So it's no longer just red and green. It has the blue component. If I bring this down and put an offset on it, I can see if I look at just the red channel, that's centered right here. Green channel looks identical to it, but the blue channel has only half of a distribution. and it's a little bit different than the other two. So that's sort of confusing for me. If I zoom in on this and look at the pixels, look at 10, I do see, well, it looks pretty good. I see blue and yellow, all different colors in here. So sort of the crazy clown colors. All right, I'm going to go back to 500 so I can look at the distribution. All right, so that's that one. So to understand that, I thought, well, okay, I'm going to look at the length of the vector. Turn these off, turn these on, and return this back up and bring this down to 0. So no offset, scaling set to 1. I have a nice uniform distribution between 0 and 1. So the length of the vector, I'll call it rho, or radius, varies from 0 to 1 uniformly. So that's good. And then I'll look at the angle. Well, since it's I created some pictures here. So I'm going to go back and look at the 2-element vector. If I look at that, I have a radius in polar coordinates. I have a radius and an angle. And so I can have this radius varying between 0 and 1, or it could be set to just 1 in the two cases. And then the angle could go this way, between 0 and 180, or the other direction, between 0 and minus 180. And with that, I can access any point within a 1 unit circle in this area. All right. Now, the other case, if I look at a typical spherical coordinate system, and I got this example from my old calculus book, you have a radius, and then you have a angle, theta, in the xy plane, another angle, phi, for the going up into the z dimension. The angle theta could typically range from minus 180 to plus 180 degrees, and then phi could either go from, might typically go from minus 90 up to 90. If we're varying the radius randomly, it would vary from 0 to 1. So the next thing is I wanted to look at the angle for this three-dimensional number. And so the first thing I thought was to look at the angle between the angle in the xy plane. So if I look at that one, I have a tangent 2, and then dir, I can access the y component of the dir, 3-element vector, and the x component. Okay, divide by 360, and I have an offset over 2. All right, so let's look at that. Turn these off. Okay, I'm going to bring this over and just leave this one all the way up. So this ranges from minus 180 to 180 degrees. So when I bring my offset over, it fits perfectly in here. So that's a uniform distribution in the xy plane. But what about the z plane? Okay, so that one is a little trickier to get at that angle. If I look at my system again, I can see that if I take this length down here, the projection of the vector onto the xy plane, which I've already got from the coordinates, I could use that as one of the inputs to the arctangent function, and then I could use my z distance as the other input to the arctangent function. So that's what I did. So if I look at this, I've got the length of a 2-element vector, and I put in dir3i of v dot y and dir3i of v dot x into that 2-element vector, took the length of it, and then for the second element of this arctangent, I gave it dir3i of v dot z. Okay, so those are the two things. So this is the same as that line I just showed you, and then this is the z dimension going up. So I give it those two elements and divide by 90 degrees, times I. And let's look at how that came out. So that gives me a nice uniform distribution. Now I would have thought that I should divide by 180 degrees so that I could access any location in the three-dimensional space, but I can't. I can only access values that are up in the positive z dimension. I can't access any values down in the negative z, which goes back to the original function. When I have dir of 3, when we got to the blue, it only goes in the positive direction. If I give an offset to these, the red and the green go in both directions, but the blue only gives me values in one direction. I don't get any negative values for the blue. So the blue only goes towards the positive z direction. Okay, not sure exactly why that is, but that seems to be the way it was designed. Okay, when I look at this one, I get this sort of, set this back like that, but I get this sort of distribution, and then I can see that it's, the blue is over here. It only goes in one direction again. Red and green go in both directions. If I look at the length of the vector, and I'll set to this one, the length of the vector is always 1. So the whole vector, and this includes the x, y, and z components of the vector, that is always 1. Okay, and then if I look at the angle, first in the xy plane, that goes from minus 180. I'm dividing by 360 here, so that goes from minus 180 to plus 180. All right, and then if I look at the same thing as I did before, the length of the x and y, and then use that as an input to the arctangent, and then take z as the third input, I get my value that ranges from 0 to 1 again. Uniform distribution, but I'm dividing by 90 degrees, and so it's only looking at the top half of that vector. So you can only get stuff in the positive z direction, nothing down here in the negative z direction. I'm not really sure why they decided to do it that way for the three-dimensional one. You can't just add these to a color, for instance, and expect it to vary randomly. You need to do some extra tweaks. The red and green, you can add that to a color, the red and green values, but you need to generate your blue value some other way if you want to add random noise to a color vector. It may have to do with normal vectors, which would probably only vary that way, so maybe it has something to do with that, but I'm not really sure at this point. Maybe I'll figure it out later. I want to look at one more thing, and that is the interpolation methods. So if I look at my diri, I'm going to change that to an S-curve interpolation. I'll scale that back down, bring it up like that, so that's this distribution, and that's what I get. It's a nice smooth interpolation. Looks, pretty good. This would be something that you could add to a coordinate system because it's 2-vector and coordinate systems are 2-vector. So if you want it to vary uniformly in terms of having a random value added to coordinates, this would be a good choice for that. Now I want to compare that to the 3-element vector version of that. For the 3-element version, first thing I notice is that the blue color sort of dominates. Now I'm going to change to the SC version of this, the S-curve version. And the first thing I notice are these vertical lines. If I change this to look at just the X component, I see I have these vertical lines here. If I switch over to the Y component, I'll just put that on the green channel. That has the vertical lines. And then I'll look at the Z component. The Z component does not have the vertical lines. So the other two components have these vertical lines in them. And so if I wanted to add this to a color, it wouldn't really look that good. These vertical lines sort of add an unwanted type of noise to those. And that's in all of the interpolation methods. So if I look at SC, I see that. If I look at CS, it's not as noticeable, but I have an artifact down here. So I'm not sure. I think there may be a bug in the interpolation method used for this. And so this seems like an artifact that shouldn't be here in this noise. If you do want to create a three-dimensional noise, you can do that. To create a nice smooth three-dimensional noise, I can start with the two-dimensional version of this, and then I'll just cast this as a three-element vector, dir cs, with that one. I could add like .x here, and then a dir cs of v .y, and then for the final value I will take dir cs of v, and this time I'll add a w to it, and then .x, and let's see how that looks there. So now I have a nice uniform distribution of my three different values of color, and the x is far enough away, hopefully, that it won't be correlated with the other x value. I could add a color to this by adding a vec3 at, let's just do like 0.7, 0, 0, so a reddish color, and go with that. And then it varies around that, and I can control how much noise is added to this. And if I set this up to a large value like 300, you get sort of red with a little bit of random color added to it. Let me know if you have any comments or questions, and thanks for watching.